Hi, I'm Ed Sperling. I'm the editorial director of Low Power High Performance Engineering. I'm here with Gary Patton from IBM. We're starting to get into the realm of finFETs, but we're also dealing with lithography, which doesn't exactly work with finFETs as we start pushing down the Moore's Law roadmap. What comes next? What has to happen? And what has to fall in place for all this stuff to work as we plan?
So, we're continuing to drive the extension of immersion lithography. It's clear that, there's still a lot of innovation that's required before EUV is ready. We pioneered the work with ASML on bringing in basically the flexible light source, which enabled source mask optimization and improved the lithography at the 14 nanometer node. But going forward, we're looking at other techniques to extend the lithography besides, brute force double patterning. The use of sidewall image transfer is a great technique to apply to the finFET process, where you've got, very regular patterns that you're trying to deal with, and you avoid the overlay issues that you have with double patterning. And then we're working on extending lithography beyond that using things like block copolymers for directed self-assembly, which allow you to avoid triple and quadruple patterning as you get to 10 and 7 nanometer.
The goal here, to a large extent, is an improvement in price and performance and also power. But power is probably the newest part of this whole thing. While we've talked about it in the past, it's really important now. How much do finFETs and the future versions of finFETs really buy us?
finFETs offer tremendous potential for improving both power and performance, but very key is how the finFET structure is engineered. It is very easy to lose all of the power performance benefits of a finFET due to the profile shape of the fin, due to issues of junction isolation, due to issues of variability of fin height. So all of those have to be very carefully optimized to be able to achieve the true benefits of a finFET structure.
So what you're saying is not all finFETs are created equal, and you really do have to work at the structure going forward.
Yeah, absolutely, and we're working very hard with our partners on how to optimize that. We've been working on finFET devices for over 10 years, and we understand the challenges. Also for our own business, we're focused very much on SOI for our finFET devices. The SOI wafers give you built-in fin height control, and by definition, you don't have an issue with junction isolation.
Do the current materials that you're working on have a long life? Bulk CMOS seems to have run bulk CMOS seems to have run out of road. Therefore, we're now using fully depleted silicon on insulator. What comes next? How long does it last? And how far do we actually see?
Yeah, I see finFETs extending us, at least into the next decade. Will we have to bring in some new innovations, integrate alternative materials into the finFET structure, such as germanium, 3,5 materials? All of those things are things that we're looking at from a research perspective to be able to extend. And then beyond that, I expect we'll be looking at new, very novel materials such as carbon nanotubes, which are really a variant of a finFET. Instead of several fins connected together in a device, you've got several carbon nanotubes connected together. There are some significant challenges, one of those being purity of the material. Roughly 30% of the carbon nanotubes are metallic, and those have to be filtered out because you wouldn't want one of those in your device. Just in the last year, we've made probably about an order of magnitude improvement in the purity of our carbon nanotube production. The second big challenge is placement. We announced a big breakthrough in the last quarter on that. Using patterned wafers with silicon dioxide and hafnium oxide, we're able to place carbon nanotubes where we need them and actually make fairly large circuits now with carbon nanotubes, roughly 10,000 circuits, or basically 1 billion carbon nanotubes in a square centimeter. So we've made a big step forward in the ability to both get pure samples as well as place these where they go. Now, I expect there's still, obviously more work to do to get them ready for manufacturing, but that's what long-term research is about. It takes literally 10 years or more with major innovations to get them ready for the development phase.
Shrinking feature size has always been about shrinking the transistor, but the other problem that we run into is when we start shrinking the wires, it's a lot harder to get signals, electricity, electrons through those wires. We start ending up with RC delay both in the wires as well as in the interconnects. What's the solution there? Where do you see that going?
Yeah, clearly we're doing a lot of work on improved liners and cap films. Those are significant detractors to the resistance of a copper line. We're also going to higher aspect ratios, so in the smaller dimensions we can get more copper into the structure. But beyond that, we're really talking about nanophotonics, and we have a big push in IBM. We had a breakthrough last quarter on nanophotonics, the integration of nanophotonic elements, waveguides, modulators, demodulators, into an integrated CMOS chip, and basically optics gives you a significant improvement in the ability to send signals around the chip at low power and at higher speeds.
What node do you see that starting to enter into the design?
Well, we're already starting. We've demonstrated prototype parts today, and I can easily see that being integrated into any particular node because it's very compatible. We've demonstrated it on 90 nanometer, for example, and it could be introduced at pretty much any technology node.
Okay. So one other solution out of all this, you have fully depleted SOI, you've got FinFETs. Another third option is to stack die so that not all of your chip is basically running off the most advanced node. Where do you see that? Where are we in the development of that? Is it starting to become real? And where does IBM actually see that being used?
Yeah, we see tremendous value in 3D integration. That's clearly a very big step in the ability to change the dynamics and how you architect a system. You can really come up with some very unique and new designs by being able to check chips. And we have a major effort in that. I can't say exactly what node we'll introduce it in, but I can just tell you that we have a very strong push in this area.
Gary Patton, thank you very much for your time.
You're welcome.